Exercise 104. So we have talked about the construction of this ring R, which we define to be the functor R applied on OC, which is also because of OC quotient by P equals OK quotient by P. Sorry, OC quotient by P equals OK bar quotient by P. This is also the same as OK bar quotient by P. And when this is characteristic 0, we write its elements as X upper index. While when this is OK bar quotient by P, we write this characteristic P, we write that X lower index, and this map is just modulo P component wisely. Okay, and then what did we talk about? We talked about this inverse limit topology. R is the same as the valuation topology. On R, sometimes we call it over the weight ring, we call it weak topology. So here it's okay, just call it valuation topology. Okay, the valuation is defined, as recall, over X is defined to be the valuation topology of OC. Let me write OC maybe, and then X0, because this is in OC. And you can also, where there is no confusion, just write Vx. Let's prove this. Actually, you can call it a theorem. So the ring R is a complete valuation ring perfect double characteristic P. With the valuation defined as above. And in particular, let me say, so this VC is normalized by valuation over P is 1. And with maximal ideal M equals that's median of MR X in the fraction field of R such that valuation of X is positive. residue field. K bar. Residue field K bar. Furthermore, it is equipped a natural continuous action of GK0 given by GX and component wisely. Okay, let's do the proof. Notice that the valuation of this R, because we are defined to be the valuation of X upper in X0. This is in OC or in OK bar, and so the image is of rational number positive union with plus infinity. This is the valuation of 0, and those comes from because you're taking an algebraic closure. So when you're taking as you could imagine, when you're taking roots of the unity of P, then for example, yeah, then you got those valuation rational numbers. And the reason this is the image is because this map is onto because all the p-th root is algebraic, give you algebraic closure, give you algebraic extension. Okay. We also have, so this valuation is plus infinity if and only if this x naught of 0 is 0 and if and only if x is 0, right? So this is because, yeah, just by definition, this is telling you the p-adic, the extension of p-adic valuation over x0 is plus infinity, and so x0 is 0. And then, so what we are doing, we will check this v is really a non-Schmidian valuation, okay? This way of xy equals v of x plus v over to see that with valuation just need to check with x plus y is bigger or equal than the minimum vx vy. Sometimes we call it ultimate valuation for any x and y r. So we may assume they're not 0, otherwise this is trivially true. Then In particular, this cannot be 0, otherwise it's again both 0. And now notice Vx is just Vx of 0 equals p to the power n times v of x n. And so you could make vxn as smaller as you want when you make n big enough. So this implies that there exists n big enough such that, I don't have to put big enough, there exists n such that this will be smaller than 1 and both x and y are smaller than 1. By definition, we have the nth component of x plus y is defined to be, if you recall the definition, the limit m goes to infinity, x plus m plus yn plus m together to the power p to the power m, right? And so this is just congruent to xn plus m. What did I write? Maybe I should write here. Let me think. Yeah, it's okay. I write this, no problem. But let's say just the lift of m plus lift of m plus n. Particular xn plus m is a lift of an x n plus m bar. Yeah, plus y n plus n. Yeah, the reason we should not write that is because we haven't defined what it is. Wait. Yeah, no, it's okay. Yeah, we can define like that. So anyway, this is congruent to this modulo p. Okay, and so the valuation of x plus y index n is bigger or equal than the minimum let me put more precisely. So this means this equals x plus y plus m plus p times some integer. Let's call it lambda. So for some lambda in ck, or just here, maybe I use c, cp flat, c. Did I write ck or c? C. And so this is bigger or equal than the minimum of x plus m. Valuation of x plus m, valuation of 1 plus m. Of course, I could change it. I just put 1, no problem, because this is always bigger or equal than 1. And if I make it smaller, of course, it's again bigger or equal than the minimum, because it's even bigger or equal than, right? Minimum of st, bigger or equal than the minimum of st is also bigger or equal than the minimum of s minus 1, t minus 1. Right. That's the philosophy. So we have this. This is bigger or equal than, because we have assumed that both already have valuation smaller than 1. So the minimum of this 3 is the minimum of the first 2. Wait, what am I writing here? Yeah, this is xn. Sorry, this is xyn. Because xn is defined to be use xn plus m and then reason to p to the power m, p to the power m, and then pass to the limit. It follows that v of x plus y is bigger or equal than the minimum of v of x. This seems like a small trick to remove the possible modulo p thing, right? And now recall in the last exercise we have proved, so 103 maybe, or 102, I'm sorry, I forgot. We have proved that, I guess 103. We have proved that the value the elements whose valuation bigger or equal to p to the power n is exactly the kernel of theta as sheet the map from R to OC quotient by POC. And this tells you that topology is complete. So the topology, the valuation topology is the inverse limit topology, which is complete. Now, because R is a valuation ring, R is a domain, we can consider frank R fraction ideal, which is actually R of C instead of R of OC. Which is again the tuple of elements. Now now not necessarily in OC but in C, such that reason to the pth power equal the evaluation V extends firstly what I want to say, is it obvious that this fraction ideal is R of C? I put this as a sub exercise, okay? Fraction ideal C. So firstly, you just have to show that this is itself a field and this is the smallest field. Right, if you want to really invert, make the field at least for x upper 0, you have to have its units, you have to have its inverse, and then the first element have to taken from C, the fraction ideal of C, and then you will see that, okay, this is indeed a field. Then that's it. So the valuation we extend to fraction ideal R by the same formula. Will x equals will x 0. Frank R is a complete non-Schmidian. Complete non-Archimedean. Perfect field. Characteristic P with real integer. Those have valuation positive, non-negative, sorry. And then obviously the maximal ideal is then M of R it's positive valuation. And then what is the residue field? Let's check the following map. From R we map it to K bar quotient by P, and then from here you can continue quotient by maximal ideal, which is isomorphic to K, and because this P is contained here, maximal ideal of OK bar. So this is surjective. And so let's say theta zeros, and as we remarked, this is surjective, and just check what is the kernel. Kernel is exactly R. There is a continuous Galois action on OC, and so it has a continuous Galois action on R through this action on component wise, because if you check the valuation, you just check this valuation on the first component, and so it's the same as checking the continuity inside OC. Okay, now second exercise, important. There exists, let's call it a proposition. This is a proposition. Okay. So let me put a question. How can you embed can you embed K bar into R? Is it possible? And then the Witterian WK bar embed into WR. This is something, well, if you know, this is very commonly thought in many places, but to forget this question, let me just state this exercise and we prove it. There exists a unique section let's call it small s from K bar to R of the map from R to K bar we just constructed. Oh yes, which is actually surjective because this is a residue field, and we can even describe. So take any element A here, I'm going to map it to, so A is in small K bar, algebraic element over small k. Particularly taking the p nth root, this is still element in K bar because it's algebraic over A. And let's take a Teshmiller lift of it. Then it is an element of W of K bar. Right, this is inside the Teshmiller lift. W of K bar, which is actually the maximal ramified extension. The real integer of the maximal ramified extension. And so now it's in OK ramified, in particular it is in OC. And then I take the couple of this. As I described, so this is the Teshmiller lift, which means this is a p to the power minus and 0 in W of K bar, which is this. Okay, proof. So this action is ring homomorphism. I claim this is part of the exercise. It's important, let me add it, which is a ring homomorphism. Proof. One can check a to the power p to the power minus n plus 1 to the power p equals a to the power p to the power minus n. So this is easy because actually what it's saying is that Frobenius, right? Reason to the p's power, okay, let me find. Corresponds to, yeah. So this corresponds to the Frobenius. This corresponds to the Frobenius and the width vector of this. Which is, in the characteristic p case, just reason to the pth power component wise, and this is just this. Right, this is this. Good. Thus, this a to the power p minus n n is an element in R. Because it satisfies this transition map, right? So indeed, we at least this is well defined. And then let's check theta 0 with intersection. This is indeed the case. So let me write there like this. We have theta 0 from R to K bar. And then we constructed a map from S at call it S. What we do is that start with A here, then our map, we constructed a tilde here, right? The tilde is by our construction, this one. A to the power, P to the power minus N. Right? And then this, when you map it to theta 0, this is just A, because it n equals 0, this is just A. And then notice this A as attached mirror lift modulo P, this is congruent to A. And so this tells us set at 0 S equals identity on K bar. So it's mod P already congruent, not to mention mod maximal ideal. So what we're left to do to check it is a ring homomorphism. We are left to check is a ring homomorphism. Okay, so A plus B is mapped to this A p to the power minus n, mapped to A plus B to the power p minus n. Right, and A is mapped p minus n, B is mapped b to the power p minus n, and A times B is mapped times b to the power p minus n. And then you check. So the question is now, is this plus this in R equals this? If this multiply this in R equals this, right? But what do I want to say? So for the multiplication, there is nothing to say. Tashmiller lift is multiplicative. This is easy. So for the addition, so actually what you have to check is that what you have to check is that is the Tashmiller lift of A plus B to the power p minus n equals the limit m goes to infinity A to the power p minus n plus m. But this is also the same anyway. Plus b to the power p minus n plus m, reason to the power p to the power m. This Tashmiller lift is also additive. Wait, is it? Yes, because this is only first position 0, so this is actually indeed limit m goes to infinity A to the power p minus plus m plus b to the power p minus plus m, and then bracket p to the power n. A and B are the characteristic P or 0? A and B the characteristic P. And so it's the same as the same as m goes to plus infinity a plus b to the power p minus m plus m, and then raising to p to the power m, then it's just a plus b to the power p minus m. I didn't see any problem. I don't even have to pass to the limit. Seems too good to be true. I'm sorry. Same, this is okay. As I said, in particular, this is telling you this. Okay, could be an injective map, which is our S to R, right? Particular this induces a map WK bar injective into WR. We have this injective map because theta 0 composes the identity of K bar, and so for any x1, x2 K bar, if sx1 equals sx2, then apply theta 0 gives you x1 equals x2. Right. It's very helpful when you construct later some maps into WR, because there are many things could be embedded into this WR. Sometimes called a inf, right? WC flat. CP flat. Yeah, basically this. So the notation here is that R of CP, or here we call it OC, sometimes you call it CP, sometimes you call it C. This functor of perfection actually is the same functor as tilting of Schwartz. Third characteristic 0 into characteristic P.